Modern scientific research has led to the development of improved laboratory testing techniques, more efficient construction equipment, and better construction methods for asphalt pavement structures. These improvements in turn have resulted in the rapidly increasing use of asphalt pavement structures to serve all types of modern traffic, from the lightest to the very heaviest, both on highways and on airfields. A most important factor in the success of these structures is the design of the hot mix asphalt pavement, which is comprised of mineral aggregates and asphalt combined at a plant where they are heated, proportioned, and mixed. The formula by which these ingredients are proportioned is the responsibility of the engineer and the inspector. It is their job to design the mix to meet specification requirements and, if necessary, to modify the mix design as the job progresses to achieve an economical blend and gradation of aggregates and the proper amount and grade of asphalt to provide a mix with the following characteristics: adequate coating and bonding of aggregate particles, suitable workability of the mix to permit efficient placement, sufficient air voids in the compacted mix to provide for a slight amount of additional compaction under traffic and to avoid flushing, bleeding, and loss of stability. Sufficient stability to satisfy service requirements without distortion or displacement. Adequate pliability of the pavement to permit slight settlements without cracking. Enough resiliency to withstand impact stresses, maximum durability, and finally a high degree of skid resistance. The engineer has choice of a number of mixed design procedures. Two of the most commonly used are the Marshall procedure and the Veeam procedure. This film will illustrate and describe in general terms the performance of tests used in the Marshall procedure. A companion film on the Veeam procedure is also available from the Asphalt Institute. The Marshall procedure is a series of tests which, if properly performed, will accomplish the objectives of good paving mix design. The Marshall procedure for designing hot mix asphalt paving may be used for laboratory design and for field control of mixes made with asphalt cements. It has not been standardized for mixes containing liquid grades of asphalt, nor for mixes which contain aggregate exceeding 1-inch maximum size. Tests are performed on specimens made from prepared aggregate samples and varying proportions of asphalt cement. Principal features of the Marshall method that accomplish the design objectives are a density and voids analysis and a stability and flow test. Before proceeding with mix design, aggregates proposed for use must be tested to determine their conformance with specification quality requirements. These tests determine wear or abrasion resistance, presence of detrimental fine dust or clay, soundness, and other aggregate qualities. The gradation of the aggregates must also be established to determine whether they can be blended to meet the gradation specifications. Aggregate samples from all proposed sources are dried to a constant weight at a temperature of 230 degrees Fahrenheit, freeing them from moisture and facilitating later separation of the material into various sizes. Specific gravity tests are then made upon samples of the mineral aggregates, mineral fillers, and asphalt. These data are used for the calculations of air voids in the test specimens. The test shown in this film is for fine aggregate. Data obtained from these tests should be kept on appropriate forms. Separate forms are used for recording data obtained from other tests described later. A washed sieve analysis is then made of representative samples of all aggregate and filler samples. A blend of aggregates can now be computed which will produce the desired mix gradation. For preliminary mix design, this will usually be a blend of the various aggregates that will result in a gradation approaching the median of the specification limits. A blend of aggregates for one trial mix series of the desired gradation is then prepared. The aggregates from each source, except for the mineral filler, are blended in computed proportions to produce the total amount required for a complete mix design. The blended aggregates are separated into several sizes by dry sieving. Washed sieve analyses are repeated for representative samples of all sized fractions. Relatively small batches are then prepared by combining computed proportions of each of the separated fractions. Each of these batches, when combined with the proper amount of asphalt and mineral filler, produces enough material for the preparation of a test specimen. It is generally desirable to first prepare a single trial size specimen in order to arrive at the proper weight of aggregate required for a test specimen of the proper dimensions. To prepare the test specimens, the prepared batches of aggregate must be heated to proper temperature in a constant temperature oven. The asphalt must also be heated, either in an asphalt heating kettle or by other suitable means. After aggregates have reached the proper mixing temperature, a heated mixing bowl is placed on a balance and tared. The heated aggregates are transferred to the mixing bowl and a crater is formed in the aggregates. The asphalt cement is weighed into the aggregate mixture in accordance with previously computed accumulative batch weights. Aggregates and asphalt are rapidly and thoroughly mixed, preferably in a mechanical mixer or by hand mixing, until all aggregate particles are thoroughly and uniformly coated with asphalt. A compaction mold assembly is heated in boiling water. Upon removal from the water, it is thoroughly dried and a paper disc is placed in the bottom to prevent the specimen from sticking to the base plate. The completed mix is transferred to the mold assembly. The mix is spaded lightly around the perimeter of the mold and smoothed to a slightly rounded shape on top. The temperature of the mix just prior to compaction is checked. Compaction temperatures also are usually established to provide a specified viscosity of the asphalt cement. The sample and mold assembly are placed on a standard compaction pedestal, which consists of a wooden post of specified dimensions capped with a 1-inch steel plate. The pedestal must be free from movement and securely fastened to a rigid floor slab. Compaction of the specimen is accomplished with the Marshall drop hammer, with the compaction energy being supplied by a 10-pound weight falling 18 inches. The compaction face of this device is heated prior to use. The face of the hammer should be held as nearly parallel to the base of the mold assembly as possible. The required number of blows are specified according to the type of traffic the mix is being designed to accommodate. The mold assembly is then taken from the pedestal. The extension collar is removed from the mold, the paper disc removed from the specimen, and the mold is inverted. An equal number of blows are then applied to the opposite side of the specimen. After this, the collar extension, the paper disc, and base plate are removed, and the mold containing the specimen is cooled to room temperature or until distortion will not occur when it is forced from the mold. The specimen may be cooled more rapidly by immersion in cold water. The specimen and mold should be placed in a plastic bag to prevent water from being absorbed by the specimen. After cooling, the specimen is removed from the mold using an extrusion jack or an arbor press. It is given an identification number and placed on a smooth, level surface. Normally, triplicate specimens are prepared in this manner at several asphalt contents. A range of asphalt contents is selected, usually in 0.5% increments, so that some specimens will be above the estimated optimum asphalt content for the mix, and some will be below. After cooling to room temperature, the specimens are ready for testing. Bulk density determinations are made by first weighing specimens in air and then weighing them while immersed in water. If specimens are porous and absorb water, it is necessary to coat them with paraffin before immersing them in water for weighing. Specimens are then brought to a temperature of 140 degrees Fahrenheit by immersing them in a constant temperature water bath for not less than 20 minutes, after which they are ready for the Marshall stability and flow test. The total elapsed time between removing the specimen from the water bath and completion of the test should not exceed 30 seconds. Upon removal from the water bath, excess surface moisture is removed from the specimen by blotting. It is then placed in the center of the lower Marshall stability braking head, and the upper braking head is fitted into place. The assembly is centered in the loading device. The flow meter is placed over the guide rod and the initial reading on the flow meter taken. The testing load is then applied at a rate of 2 inches per minute. When the load begins to decrease, the point of failure has been reached. The flow meter is lifted from the guide rod just as the load begins to decrease. The maximum load required to produce failure is read from the calibrated proving ring dial gauge, converted into pounds from a calibration chart and recorded. The maximum load in pounds required to produce failure is recorded as the Marshall stability value. The final reading on the flow meter is recorded, from which is subtracted the initial reading. The difference is the Marshall flow value, or deformation of the specimen in units of 1/100th of an inch, between no load and a maximum load. This completes the testing operations. Computations are then made for corrected stability and flow values, density of the specimens in pounds per cubic foot, the percent of air voids in the compacted specimens, and the percent of voids in the compacted mineral aggregate structure, which are filled with asphalt. Average values for test properties of the triplicate specimens at each asphalt content are then plotted on appropriate charts. The optimum asphalt content for the mix is then established by averaging the asphalt content at which maximum Marshall stability occurs, the asphalt content at which maximum density of the compacted specimens occurs, the asphalt content at which there is a specified percent of air voids, and the asphalt content at which a specified percent of voids in the compacted aggregate structure are filled with asphalt. Specified percentages mentioned in these last two items will vary, depending upon conditions for which the mix is being designed. After establishing the optimum asphalt content in this manner, certain test values are read from the charts at this optimum asphalt content. Values obtained are compared with established criteria for test limits such as these from the Asphalt Institute Specification Series Number 1. If the test values obtained from the mix design tests fall within the criteria for test limits, the mix will be satisfactory for its intended use. Marshall test methods have been standardized by the American Society for Testing Materials and are described by ASTM method D1559. Complete and detailed procedures for performing and interpreting the results of the tests shown in this picture are found in the Asphalt Institute publication, Mixed Design Methods for Hot Mix Asphalt Paving. Careful adherence to proper mixed design procedure is one assurance of an economical, safe, and durable asphalt pavement for all traffic requirements.